Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everybody. It's my pleasure here to introduce Professor Figueiredo. So I'm Arnaud from ELIS, the European Laboratory of Learning and Intelligent Systems. And basically here today we have with us Mario Figueiredo, who is the IST Distinguished Professor and holder of the Feedzai Chair on Machine Learning at the Instituto Superior Técnico IST, the University of Lisbon. And he also serves as the group leader at the Instituto de Telecomunicaciones, and is a director of course, the ELIS unit in Lisbon, which we are very happy about. I'll keep it short, but otherwise he's a fellow also of ELIS, as well as IEEE, IAPR, and EURASIP. And his talk today will focus on the why of AI, uncovering cause and effect in observational data. And now I give the floor to Mario. Thank you.
Thank you very much for the introduction. It's a great pleasure to be in this series. So I'm going to try to share my screen. Okay. So good afternoon, everybody. So this is a talk about which I decided to call the why of AI. So in the underlying idea is that we need to be able to uncover cause-effect relationships in observational data, and I'll try to convince you why this is extremely important. So this is not a very technical talk, although especially in the beginning, but then at the end there'll be a little slightly more technical aspects, but nothing very, very difficult to follow, I hope. And I guess, so as Arnaud said, I'm a professor at Técnico in Lisbon, which is the engineering school of the University of Lisbon. I'm also at the Institute of Telecommunications, and I'm also part of ELIS, in particular the Lisbon unit, of which I'm the director. Okay, so causality. So this why, the why word somehow underlies the idea of causality. And on this topic, I usually like to cite these two very famous philosophers. So Baruch Spinoza, who in 1663, so in the 17th century, wrote a lot about this issue. And the famous sentence is this one: nothing exists of which it cannot be asked, what is the cause? So causality, or reason why it exists. So its causality has been in the minds of philosophers for a long time. Not long after this, Leibniz, very famous scientist and philosopher, wrote this sentence: we can find no true fact, so nothing that happens without there being a sufficient reason why. So the word why is always appearing. It is thus and not otherwise. But then, although most of the time these reasons are unknown. And so actually this red and blue parts of this sentence kind of summarize the topic of the talk and the topic of a very large field, which is called causal discovery, which is to uncover these reasons why things happen. So what are the cause-effect relationships that underlie what we observe? So actually, causality is quite a deep and controversial topic. So philosophers have discussed it and debated for a long, long time. I always also like to quote this sentence, very famous sentence from Bertrand Russell, who at the beginning of the 20th century wrote this sentence that claims that the law of causality, I believe, like much that passes muster among philosophers, is a relic of a bygone age, surviving, like the monarchy, only because it is erroneously supposed to do no harm. So he was defending the idea that causality is not something that actually exists. It's something that we tend to interpret things using cause-effect relationships. that actually do not exist. And he was using the idea that classical physics, there is no notion of causality. But much more recently, so this is 2022, so 4 years ago, very famous physicist Carlo Rovelli, who's been discussing these topics for some time now, has this very interesting article called Back to Reichenbach, and we'll talk about Reichenbach in a second, where he claims that this notion of direction of time, which is a very important notion in all of philosophy, not only in physics, to understand it and to study it, you need the notion of cause. And so he recovers, well, not only him, but he's this emblematic of this thing that you need the notion of causality. So causality is a very important notion. So these are to give an example of two extreme positions where causality just does not exist, and at the other end, causality is a fundamental concept. So it's a controversial topic. So let me just start. A lot of people, probably some of you or many of you have seen this image. This is a very famous plot that shows it's a plot that shows chocolate consumption in kilograms per year per capita versus the number of Nobel laureates per 10 million population. So if you look at this plot, you show, well, these things seem to be extremely correlated. So maybe it is that consuming a lot of chocolate makes people very smart, and so you have a large population with smart people, and so it's more likely that you have more Nobel Prize laureates. Of course, we know that's not the case, but plots like these kind of suggest that there is some cause-effect relationship between chocolate consumption and Nobel laureates. Of course, the true reason is that wealthier countries, typically people eat more chocolate, and they also have more science funding, and so they're more likely to produce more Nobel laureates. Of course, this is usually summarized in the very famous sentence that says correlation is not causation. And this was just to motivate this sentence that says, of course, standard machine learning. Let's go now start looking at machine learning. It's excellent at prediction. So all classical machine learning methods are excellent at extracting correlation between things that we want to predict and things that we observe. But typically they do not include an explanation, no why. They typically will try to, it's very hard to come up with a convincing answer to the question, why did you predict that? And that's a whole field called explainable AI or interpretable AI, interpretable machine learning. But let me give you an example of why this is important. This actually, I forgot to mention this paper. This is from the paper that I'm going to show next. So suppose you have this machine learning problem where you want to distinguish stars from moons, and you have this small training set of stars and moons. It's a label data set, so it's very classical machine learning problem. And then once you train some model, you can compare it to what a human would do with a new test set. Now you have a test set that follows the same distribution. So a human says, okay, these two first examples are stars, the second examples, the third and the fourth example are moons. The machine learning model will say the same, so everything is okay. But suppose that these are the examples. Now, in these two examples, the human would still say these are stars, the machine would say these are moons, it's giving it label B. And the third and the fourth, the human correctly says they're moons, but the machine says they are stars. It gives it label A. What's going on here? So what is going on here is that the machine learning model, learned how to distinguish stars from moons, not because they look like stars or they look like moons, but because in the training set, all the examples of stars were either in the bottom left corner or in the top right corner, and all the moons were on the bottom right corner or on the top left corner. And so the machine generalized, but it did something that's sometimes called shortcut learning. It learned, it happened to be correct for the training set, but it's not correct, it doesn't generalize well. And the one way to uncover these types of problems is by having a cause-effect relationship that tells me I'm classifying these as whatever, moon, dog, whatever, because, so there's the fundamental word because there's a cause, which is its shape, its position, whatever. So it's very important to understand cause-effect relationships, to understand how machine learning generalizes beyond training sets, especially when there's shifts in distribution, which is this case. So standard machine learning typically has poor generalization, especially under covariate shifts. And this is all a very active area of research, how to handle covariate shifts and other types of shifts. But in this case, covariate shifts, it means changes in the features that describe the objects. So for this topic, I recommend this very nice paper from less than 1 year ago, which is a review paper on the role of causality in explainable AI. And so I'm not going to go into the details of this paper. Of course, it's a very big, quite comprehensive review. Essentially, if you're looking at the bottom of the image, we see that one application, say, of causality in this field is of XAI, which stands for explainable AI, is to critique the way explainable AI is typically done. So there's very often a lack of a causality in the sense of explaining why labels or predictions are the way they are, pointing out some pitfalls of explainable AI, the form of the explanation in the fact that they're not causal, and so on. And on the other hand, you have how can causality be used to improve explainable AI? So we can use causal tools for supporting explainable AI. Counterfactuals, which I'll explain in a second, but they are assessing causal models, is explaining how they behave. So this is kind of a very important identification between explaining and understand and providing a causal discovery, a causal explanation. So finally, another reason why AI needs causality is because if we're trying to replicate somehow human cognition and human reasoning, so causal understanding and causal reasoning is a defining characteristic of human cognition. So it's impossible to get close to what humans do, or even higher, more sophisticated animals, such as chimps in the image, without going into this causality and the causal understanding of the world direction. This is a very interesting paper, which I also highly recognize, by Marielle Godou and Alison Gopnik. Actually, Alison Gopnik is a very famous cognitive psychologist. Which is a review paper on the development of human causal learning and reasoning. And so this first sentence says it all. Causal understanding is a defining characteristic of human cognition. And this example on the right just shows that, like the chimp on the tree, he expects that if he shakes the branches, then it will make the fruit fall, so that he has some notion of a cause-effect relationship between shaking the branch and the fruit falling. And at higher levels of causal reasoning, you have stuff like third-person causal understanding, where an agent, in this case a child, knows that another agent can cause things to happen. And so these higher level cognitive capacity in terms of causal reasoning is also characteristic of humans and of other animals. So this is very important. So if we want to have AI somehow mimicking what humans do, we need to have a causal understanding. And back to XAI, to explainable AI, I just want to, before going into the meat of the topic, let me just point out, maybe many of you have heard of this. It's a very famous example in fMRI, so functional magnetic resonance imaging, which is an imaging technique for human brains, typically was developed for human brains, which kind of allows researchers to understand what activity is going on in the brain when they're doing something. And there was a very famous experiment some years ago where some researchers put a dead salmon, so a fish which was dead, inside an MRI machine, and they captured functional magnetic resonance imaging, and they actually showed images to the fish, which was dead, and they could find some activity levels inside the brain of a dead fish. So this became known as the dead salmon effect, or the dead salmon experiment. And the idea is that the methods that people use to detect activity and to understand what's going on in the brain sometimes are just producing a lot of false positive stuff that tells more about how the experiment is designed and what it's looking for than what actually is in there. And very recently, a group of researchers put out this is very recent, I forgot to write the date, it's like a month old or something like that, the dead salmons of AI interpretability, where they claim that AI interpretability is sort of suffering from the same dead salmon artifact, where people find a lot of things. So there's all sorts of techniques for interpreting what machine learning is doing, what complicated deep neural networks are doing. And there's a lot of of things that are found in these areas where a lot of them are just artifacts of the analysis techniques that are being used, and they don't necessarily reflect what actually is going on. And well, this is not just a negative paper. They come up with a new pragmatic, what they call a pragmatic statistical causal reframing of the problem, which attempts to solve this dead salmon effect. And finally, this is the very famous, we cannot talk about causality without mentioning, of course, Judea Pearl, who is one of the seminal figures of the field. He has several books, but this more accessible book is called The Book of Why, where he distinguishes these three levels of understanding of how observations are related to each other. And so he has this basic level, which is called association, where we see, we observe, but we don't intervene. And essentially, the questions that you can ask in this case are classical statistical questions, such as how seeing something changes your belief in something else. How knowing that this country consumes a lot of chocolate changes your belief in that this country is likely to have a lot of Nobel Prize winners. So there is correlation, so there is information in that. But the kind of model that does not allow you to understand what's going on in interventions. So what if I do something? So what if you take a country and for 10 years you force everybody to eat 10 times more chocolate than they usually do? Would that create more Nobel Prize winners? Probably not, right? But to intervene, you need to know, you need to be able to intervene in the system, and sometimes it's not possible to intervene in systems. But if you know how to do it, and if you can, then that allows you to understand and to answer another level of questions that are not available, that are not accessible if all you have knowledge about is associations, correlations. And finally, if you do have full knowledge of the cause-effect relationships inside some that explain that underlie some phenomenon, let's say, you can even ask another level of questions, which are called counterfactual questions, which are questions of the sort, what if I had done something? I didn't, but what would have happened if I had done something? So I had a headache, I didn't take an aspirin, now I still have an headache. Can I ask the question, what would have happened if I've taken an aspirin 2 hours ago? Of course, you cannot go back in time to try it, but you can think about it. You can try to answer these questions, and this is a very important area also, which is called counterfactual reasoning, which has to do with questions of what if in the past, not what if in the present and future, but what if in the past. So that's why they called counterfactual. And finally, I also, for the people who want to think about causality, I really like this very little paper, very small paper. It's about, I think, 2 or 3 pages by Carl Bergstrom and Jevin West. So Carl Bergstrom is they're biologists, both of them actually, I think. And this is a paper from 2018, and let's think back of the problem of chocolate consumption and Nobel Prize winners. And so the idea that is defended in this paper is that scatter plots, the way they're shown, they carry a subtle message about causality, even if it's implicit, but it's a message. And this may be a problem for the public understanding of scientific results and perhaps also for professional scientists. So remember, chocolate consumption, Nobel Prize, number of Nobel Prize winners or Nobel Prize laureates. If you show it like this to someone who does not have a very sophisticated understanding of what data, what graphs are, it kind of suggests that the horizontal axis is the cause and the vertical axis is the effect. So this kind of plots. So for example, this is an example where this shows in horizontal axis change in housing prices in some, I don't know where this is, somewhere in the US, and in vertical axis change in fertility rate. So if you show it like this, it kind of suggests that if houses become more expensive, people will have fewer children. But there's also another explanation, which is if people have fewer children, then they have more money available to buy houses, and or less money available to buy houses, and the changing that affects the housing prices. And if you want to abstain from carrying any of these two cause-effect relationships, because you don't know which one is the true one, you just want to plot the data without giving any cause-effect message, then they suggest that we should start using these kinds of plots, which are 45 degrees. So they are agnostic in terms of what is the cause and what is the effect. This is just a cute idea. I haven't used it yet, but I think people should have in mind that every time you show data, you're giving a message, even if it's very subtle and implicit. You're giving a message, and you should be careful about cause-effect relationships, especially in things that have implications in, say, in policy or in healthcare or so on. Okay. So I cannot give any talk without an XKCD cartoon. So here's one. So here's the two stick figures talking to each other. So the one on the right is saying, "I used to think correlation implied causation," and then he said, "Well, then I took a statistics class. Now I don't." And of course, she asks, "Sounds like the class helped." Well, maybe. So and I really love this cartoon because it actually explains the fact that because something happened after another thing, it doesn't mean that it was caused by that thing. And so that although they're correlated, one is not necessarily cause of another. You need to explore further to guarantee that this is what is going on. Okay, so let's see this in more detail. This is an example that I really like. It's shamelessly copied from this book by Brady Neal from 2022 called Introduction to Causal Inference, which is, suppose we have statistical evidence that people who wake up with their shoes on are more likely to have a headache. Well, so that's correlation. So some statistics were collected, and there is evidence that there's association between these two facts, waking up with a headache and with your shoes on. So you may ask yourself, well, why is this? Does sleeping with the shoes on causes a headache? Or is it vice versa? That the fact that you had a headache and so you went to bed, you were not feeling very good, and so you didn't even take your shoes off? Or is it just a coincidence? Okay, could be a coincidence. Coincidence happen. And here we have this is where I want to mention Reichenbach. Reichenbach is essentially, so it's called the common cause principle. It's essentially the idea that there are no coincidences. Everything every pair of things that depend on each other, it's necessarily because there is some underlying cause-effect relationship. And it can be one of three things. So if two events A and B are dependent, so in this case, the waking up with the shoes on and the having a headache, if they are dependent, then it's either A that causes B or B that causes A, or there is something else that causes both A and B, which is a common cause for both. This is why this is called the common cause principle. So Reichenbach is this name that I mentioned right at the beginning that Carlo Rovelli refers to in his paper called Back to Reichenbach. So what would be this cause-effect relationship? So A causes B, like I mentioned. So maybe going to sleep with your shoes on causes you to wake up with a headache, or vice versa. Or maybe there's a common cause. You've been drinking the night before, you drank too much, you arrived home too drunk to be able to take your shoes off, and of course you woke up with a hangover with a headache. So how do you know which of these is true? Suppose now that we gonna look into this problem in more detail, and so we do some statistical tests, and we find out that the fact that you wake up with your shoes on and with a headache, and these two events are independent, given that you know if you've been drinking or not drinking. So given the status of drinking, not drinking. So in probabilistic or in statistical terms, this would be written as like this. So the probability of waking up with your shoes on and having a headache, given that you're drunk or not drunk, given that variable, is approximately, it factorizes. So it's independence is stated by the factorization. So if P of shoes given drunk times P of headache given drunk. So this is what we call conditional independence. So waking up with your shoes on and with a headache are conditionally independent given that you were drunk. So in statistical notation, this is written like this. So shoes, conditionally independent from headache, condition on drunk. It happens that this conditional independence assumption is compatible with three different possible causal mechanisms. Okay, it could be it will take like a minute or two to explain exactly why, but it could be that the thing that we have in mind, which is, well, being drunk probably causes both. Or it could, but it's also compatible statistically. Keep in mind that we don't have a notion of time, so we don't know what happened first. Okay, we just know, did it happen or it didn't happen? That's it. If we have access to time and to time order, then this excludes, of course, several possible causal mechanisms that are not, because we know we cannot go back. But so just statistically speaking, this condition dependence hypothesis or property is compatible with these three possible causal mechanisms. Mean that I had a headache, then I decided to drink a lot, and in the end, I woke up with my shoes on because of a hangover. Or it could be the other way around. I noticed that I had my shoes on, so I thought, well, I need a drink. I drank too much, and then I woke up with a hangover. Of course, only one of the three is correct, but using only statistical evidence, so knowing only about this condition dependence property is not enough to distinguish these three and to find out which one is the true. Okay, how to find which is the true cause-effect relationship. Well, if you ask a human, so suppose you have a data set of observations. So the set of observations is just a table, long table. Let's say you have 1,000 examples of drinking or not drinking, ones and zeros, waking up with shoes on or not, zeros and ones and zeros, and waking up with a headache. Well, if you ask a human, the human will say, well, obviously, the cause-effect relationship is this one, because everybody knows that if you drink too much, of course, next morning you may have a headache, and it's more likely that you wake up with your shoes on because you were too drunk to take your shoes off. And what we want to replicate in causal discovery is this procedure, this process where a human looks at the data and comes up with the correct underlying cause-effect relationship. Okay, so causal discovery is the automation, let's say, of this thing that for humans is extremely easy, which is finding out cause-effect relationships. Actually, that's it's known that children, when they're growing up, especially when they're babies, and all of our lives, we're always reasoning in terms of cause-effect relationship. We want to cause certain effects, and we're always trying to find out what causes what. There's an important caveat, which is humans know the meaning of the variables. Humans know that what drinking means, what waking up with shoes on means, what having a headache means, whereas a causal discovery method is operating without knowledge of any meaning. It operates just on a table of ones and zeros. So it needs to discover what the relationship is, looking only at ones and zeros, not at meaning of what those ones and zeros mean, because the machine does not have a meaning, a semantic meaning for what these variables. So it's not completely fair to say that this is very easy for a human. It's very easy for a human, not because the human knows how to interpret these ones and zeros, but because the human knows exactly what they are representing. And so even without looking at any statistics, a human would know exactly what the correct cause-effect relationship is, causal graph is, whereas a machine would have to resort to other types of principles to be able to do this. So how do we do this? Okay, so the classical and say the gold standard is the gold standard of science, which is formulate an hypothesis and do an experiment. And an experiment means you need to intervene in the system that you're trying to understand. So in this case, causal discovery would imply you would, for example, prevent someone from drinking, or you have a population which and you create a subpopulation and you stop all these people from drinking, and another subpopulation where you force them all to drink, and then you compare what happened in the two populations. Or you force someone to go to bed with your shoes on, and then see what happens. So you need to be able to intervene in the system to try to uncover what's going on. For example, if you force someone to go to sleep with your shoes on, you cut the dependency of waking up with your shoes on the fact that you were drinking or not. And so you can understand if this has an effect or not just by blocking this connection. So this is very well known, for example, in gene expression data, where you're trying to understand if some gene activity has causal effects on some property of the living being to which that gene belongs. So, for example, suppose you have all these plots. This is an example by Jonas Peters in the tutorial some years ago. So you have this activity of gene A, which is clearly positively correlated with expression of phenotypes. Some phenotypes say how big your ears are or something like that. And another gene, let's say gene B, which has some correlation with some other phenotype. And you want to, one way of uncovering if this is a cause-effect relationship or a mere correlation is to do something called gene knockout experiment, which is you force the activity of gene A to be zero. You knock out this gene, and you want to predict the phenotype. What should the phenotype be if I force the activity of gene A to be zero? And same thing for gene B. And now what you can do, now you go and measure. And so if, in fact, gene A is the cause of the phenotype, what you will find is that if you knock out gene A, the level of the phenotype is going to be low because you intervene in the system, you actually move the system to the left corner, bottom left corner, and so this is what you see if this is actually cause-effect relationship. Whereas if it happens that the relationship between gene B and the phenotype is not a cause-effect relationship, gene B is not directly affecting the phenotype, it's just correlated with the phenotype because there is something else that controls both of them, then what you will find is that the fact that you knock out gene B has no effect on the uncertainty about the phenotype, and you will have some values that are there, so they were not forced down by knocking out gene B. So a key, so to formalize this idea of interventions, Judy Pearl created this toolbox, let's say, which is called the do calculus, which is based on a key insight, which is observing is not the same as intervening. So just knowing that something happened is not the same as forcing that thing to happen. And the essential, in a nutshell, the idea is that when you force something to happen, you break its dependency from other things because you're forcing it to take some value or to take some property. While when you're observing something, you're observing it under the effect of everything to which it is dependent from. And this is fundamentally very, very different. So intervention in formal terms is written as do X. It just means let this variable X take some value, which as it cuts the input arrows and sets the value. So suppose you have these two variables, X and Y. And suppose that the relationship between X and Y is cause, if cause is X is cause and Y is the effect. If you want, you ask if this is the true cause-effect relationship, then the probability that Y takes some value, say little y, given that you force X to be equal to little x, is the same as that probability under the observation X equals X, because that's actually what happens. By forcing X to be X, you're not cutting its dependency from anything else because X does not depend on anything else. It just depends on its own value. Whereas if actually the cause-effect relationship was the reverse one, was from Y to X, if you force X to take some value, you're cutting the dependency from Y. And so once you cut this dependency, Y becomes independent from X. And so the probability that Y takes some value, given that you force X to take some little value, little x, is just the probability that Y takes this value, which is not the same as the one above, because they're not independent. This would be true if they were independent, but they're not. You're just forcing X to take some value that ignores the value of Y. And so this is in essence what the experiment in the gene knockout example in the previous slide was. You need to do experiments, intervene in a variable to distinguish if this is the cause-effect relationship or this one by looking at the statistics once you do nothing or you do force X to take some value. And you force Y to take some value too, if you want to also test the other direction of causality. Okay, so back to the idea, cause-effect disambiguation, let's say causal discovery interventional data. The problem is that these interventions are often impossible. Just think that you're studying some phenomenon from the past. You cannot go back to the past and intervene. It could be impractical. For example, think of a policy intervention which implies changing tax levels or taxation levels or unemployment benefit or something. It's very hard to experiment with these things because you need to intervene in societies, so it's very impractical. Or it may be even unethical. If you want to intervene in a headache, for example, you would need to, say, hammer the person on the head to give him a headache. which of course is unethical. So some interventions are actually unethical because they will cause harm. And this is very common in social sciences, in medical applications, where some interventions are unethical. And so this forces us to think about this cause-effect discovery, cause-effect uncovering discovery directly from observations. I think I've noticed I'm moving a bit slowly. So, this when we have this more general situation where we have more than two variables, there's a more general framework which I'm going to go over very quickly, which is something called, maybe most of you know about this, directly the cyclic graphs, which is now we don't have only two variables, we have a bunch of them. They are related. So there's the non-descendants, the parents are those that are directly connected to a given variable. And then the descendants, which are those that are accessible from these by following the correct arrows. So a structured causal model is a model that makes explicit how these variables are related to each other using a collection of functions and a collection of random variables. It says that simply that the value that xj takes is some function of its parents, in this case the red ones, plus some exogenous perturbation, which is random, which is supposed to model everything that's beyond the direct deterministic dependency on a variable on its parents. So these exogenous variables need to be mutually independent. So they're all in these models. And they model and explain the fluctuations in the system, everything that's random in the system. And each of these functions is a causal mechanism. Let's say its name. This is so in biological applications, for example, this can be really complicated. So on the right, you have the gene regulatory network of the human brain. There's a Nature paper from 2023 that has several thousand nodes. So there's cause-effect relationships between lots and lots of tens of thousands of genes that express themselves and have effect on expression of other genes. It's a very complicated network. On the left is something else which is from a military application, but I'll skip this. I'll skip these because I'm running out of time. And the main question here is: can we recover one of these graphs just by observing samples, or even if you know fully well the joint distribution of all these variables, can you recover the graph, the structure of the graph, which nodes are connected to which nodes, the functions and the distribution of the exogenous variables? Now, the answer is, well, in general, you can, but only up to the Markov equivalence class. You can only do it, but you cannot only from this knowledge of the joint distribution of the variables. Even if it's perfect knowledge of the joint distribution of the variables, all as far as you can go is up to this collection of possible graphs, which are not distinguishable using only statistical information. So the way to do is with interventions that we already saw, but I'm going to skip the general notion of intervention. I'm going to jump directly to an example. This is a classical case, not an example, it's a case, which is, suppose you want to study the effect of X on Y, but you know that there is some third variable, Z, which could be a confounder. Say you want to study the effect of some pharmaceutical on some disease, but you know that there is some third effect, some third variable, which affects both the outcome of the treatment, but also the selection of whether you take or don't take the medication. And so the way to get rid of these confounding effect is to do something which is called a randomized trial, which is you force X to take some value in a way that is independent from Z. So when you do P of, you want to know what is the probability of getting, say, cured, given that you took the medication, you force taking the medication in a way that is independent from Z. And so you can disentangle and you can find out that P of Y given that you force X to take some value is different from P of Y given that you just observe value. So this is a very well explained, very well illustrated example in a tutorial from Dominique Janzing and Weishalt from a few years ago. And so the idea is that you assign X randomly, independently from X, typically randomly. And the standard example in this case is something called randomized trials, which are used in medicine, in economics, in so-called A/B testing, in marketing, in website design, in many other areas. Of course, this idea that you can do this in all problems that you're faced with it's let's say too bold. Again, I have a nice cartoon from XKCD about the limitations of blind trials. So if you're trying medication, of course, no one should know if it's taking medication or placebo. This is a very well-known fact. And so this research is saying that we have designed a double-blind trial to test the effect of sexual activity on cardiovascular health. Of course, both groups will think they're having lots of sex, but one group will actually be getting sugar pills, so placebo. This is not possible. So there are lots of things that affect outcomes of, say, pharmaceuticals that are not blindable. So there's no way the patients do not know what's going on. And so this is one reason why it's very hard to get actual cause-effect relationships in social sciences and in health sciences, for example. And this is one of the reasons why I would like to mention this too, why this work that got the Nobel Prize in 2021 but to Angrist and Imbens, which is one they're seminal proponents of this notion of something called natural experiments, which I'm not going to go into details at all. Just shout out there. This is very important research. The idea is that in some situations, there are interventions in the system that were not caused by the experimenter, but they happened for some reason, that it's independent from the phenomenon that you're trying to research, to try to investigate. And they can be used as natural interventions. They happened not because you wanted them to happen, but just because they happened. And they have an effect which on the phenomenon, and you know that the choice of this thing happening is independent from the effect that you're trying to study, and so they can be used as actually interventions. It's very used in economics, in social sciences, in biology, in many other ways. So can we actually do these of uncovering cause-effect relationships only from observational data? And so yes, we can under certain conditions. And the underlying principle is something called the principle of independent mechanisms. So I usually highly recommend this book by Peter Zianding and Schalkopf, Elements of Causal Inference. This is a snapshot from the book. It says the principle of independent mechanisms. The idea is that in the case when you have only two variables, in the true cause-effect direction, the distribution of the cause and the mechanism that produces the effect from the cause should be independent. So there's modularity in the system. And to try to convince you that this is how we function in our brains, I'm going to show you a very famous example, which as soon as when you look at this image for the first time, you see what's going on. It looks like there's this very small woman sitting on a chair, but you know that women are not this small compared to the man that's standing next to her. So what's going on? Well, what's going on? Well, of course, once you think a little bit about it, you understand that what's going on is this. So the woman is far away, so that's the perspective effect seems to make her smaller than what she should be. So she's not smaller, she's just further away. Why are we fooled by the left example? Actually, this is the case for many other optical illusion examples, is that we assume, so our brain assumes, this is called the Butcher-Sher illusion, our brain assumes that the viewed object, which is the thing that we're looking at, in this case, the image of a woman, and the viewing angle, which is the observation mechanism, are independent. At first glance, we do not think that the viewing angle was somehow tailored to create this illusion. We just think that it's a general angle. And so this is, our brain actually embeds this notion that the observation mechanisms and the things that are being observed are independent things. And so we always assume that. So in the case of these simplest of all problems, which is when you have only two variables, how do we distinguish between x to y or y to x? Only from observations. If we assume that there are no hidden confounders, let's assume that we know that one of these two is actually true. And so without interventions, we're not allowed to intervene because we don't have access to interventions. So the foundational principle that essentially almost always allows to solve this problem is this idea that of independence of cause and mechanism, or the ICM principle. What do you mean by independence? Of course, there's a lot of papers about this. I'm not going to go into any detail. It's not statistical independence. It's functional independence in the sense that you can tweak, you can change the distribution of the cause without changing the effect. So one thing is the mechanism that links effect to cause. Another thing is distribution of the cause, and they do not affect each other. There have been many ways of instantiating these mathematically using information geometry, Kolmogorov complexity, many different things, but I'm not going to go into details of any of that. One very classical way of doing this is something called additive noise model, which says, okay, in the right direction, if in the right direction I can model the system in this way, so the effect Y is some function of the cause plus noise, so that's why it's called additive noise, where the noise is independent from cause, then this system is identifiable in the sense that if there is such a model from X to Y, then in general there is no such model from Y to X, and this is a very famous result by Jonas Peters et al. From about 10 years ago, which is identifiability of additive noise models. So I'm going to skip the more detailed formulation. Just give you an example. Suppose a couple of examples. This is a paper by Gleimer from 2019. Suppose you have X and Y, and you've plotted these lots of points. You do some linear regression, and the variables are Gaussian. If the variables are Gaussian, then you cannot distinguish which is the cause and which is the effect. But if they're not Gaussian, and it's fundamental property, if you do, say, linear regression under, say, uniform noise, there is one direction in which the cause is actually independent from the residual of the regression, and in the other direction it is not. And so if you're dealing with the additive noise model under non-Gaussian noise, that alone is enough for you to be able to distinguish which is the cause and which is the effect. So this was a problem that was very active, like the past decade, very, very active. So there's this very famous data set called the Tübingen data set. And it's known that data sets always help creating attraction for some field of research. So the creation of the Tübingen data set created a lot of attraction to this problem. And of course, there are lots of questions about it. So there's lots of papers in this topic. But what happened is that it is true that now there are many methods today that are able to perform quite well, quite above random choice in this data set. So around 870 something, nearly 80% of accuracy. And remember, this is a very difficult problem because these methods are only looking at data, nothing else. They don't know what the meaning of the variables. They don't know what waking up with the shoes on is or what being drunk is. They just see either ones and zeros or numbers, tables of numbers, a table with two columns of numbers, and they need to find out which of these is the cause and which is the effect. So this is a remarkable result, I think. It was extended to discrete data later on. It was extended to categorical data in my group by myself and with the help of students some years ago. I will skip this because we're running out of time. And more recently, so running out of time again, we're addressing this problem using the notion of exchangeability, which I will skip because I want to leave some time to questions. If there's questions, I'm going to skip all of these. To just highlight these, maybe not, I will skip it. I will skip all of these. I will skip all of these. I just want to highlight this paper from June of last year about these questions. So what about LLM? So everybody is crazy about large language models these days. AI kind of became almost synonymous to large language models. It's a paper published in June of 2025. The title says it all. LLMs cannot discover causality and should be restricted to non-decisional support in causal discovery. And in the abstract, they say these authors, call for the community to shift focus from naively applying LLMs to developing specialized models and training methods that respect the core principles of causal discovery. So for now, at least, causal discovery LLMs are not a solution and should not be used, at least not directly, not directly. And so with this, I will stop here and will be glad to take any questions that you may have. Back to you, Arnaud.
Yes. So I don't see any questions in the chat.
So I don't know where the questions come from, if they come.
Normally they're in the chat. But maybe in the meantime, I can ask you already a question from my side. So no questions yet. So maybe to kick it off. So can you maybe elaborate a bit on the latter part, especially with foundation models and large scale AI now being very, let's say, present in our everyday lives, how causal inference and causal discovery is, yeah, maybe relevant or more relevant today than ever before.
Yeah, so large language models are well, like I don't know who wrote like it's a stone soup in the sense that they are well actual chatbots, in the sense that in the core there's this large language model which was trained using prediction of next word prediction. So they are essentially capturing statistics of language, but then built around it. So there's all these other shell that is used to train like how should the LLM react to a question. Relevance, so reinforcement learning for immune feedback, direct optimization, all of this stuff. So these are methods that are probably closer in spirit to causal inference. Let's say to like there's well now probably it's too technical for this context, but reinforcement learning is somewhat closer to causal inference and to causal discovery because you want to learn how to act in some way to create some effect, some reward. So I guess causal inference and causal discovery is relevant for these post-training and fine-tuning of models because you want to sort of create certain behaviors and behaviors are in a sense cause-effect relationships because you want if something happens then I want this thing to cause this kind of behavior. So I think that's from causality to chatbots, let's say, to modern AI systems. On the other hand, which is what the topic of the paper that I mentioned is, can you just give data to a chatbot and ask it to infer cause-effect relationships? And what they found out, they did experiments on this, is that the results are a little bit like for humans, because these methods were not trained with in cause-effect discovery. So it's a little bit like for humans. If you give it a table of data and you tell the semantics of the data, you tell, well, this is this variable and that variable, the LLM will be great because it has a lot of human knowledge. Okay, if I give it like, if I ask Gemini or ChatGPT, I know the question in the beginning, like, okay, I have these three variables, it's drinking, headaches, and waking up with the shoes on. Even if you give it no data at all, it will, of course, it's the drinking that's causing both. But if you just give it data with no semantics, then they cannot do it because there's nothing in the training set that prepare them to do causal discovery from data alone.
Yeah, makes sense. There's no further questions yet, but then I'll ask my second and last one that I have up my sleeve, which is actually elaborating on that with respect to world models, which are inherently built in with a interventional input. And maybe, I mean, one idea that came up was if you there's also a lot about reasoning models, which is more in the classical LLMs. Maybe if you have them reason about maybe organizing a DAG, so a directed acyclic graph, and try to reason about the process, what it would be, would that maybe aid the reasoning and make it more causal? That's one thing. Or do you think that a more classical world model where basically the data also has some notion of causality because of interventions would be a better direction if you would need to choose?
I would think the latter. So I think
Okay.
the world models are a step in the right direction because a world model, in my opinion, cannot help but be a causal model. Right? It needs to because the idea is to build agents that are able to intervene in the world and to do things that cause effect. A robot needs to know what happens if I do this. Even if just from observations, and humans are extremely good at inferring cause-effect relationships from observations. You go into a room and you see something on the floor, and you immediately know that the thing is on the floor because someone dropped it, right? Although you haven't seen anything, you just because you know how the world works, so you're always coming up with cause-effect explanations for the things that you observe. So I think AI, the future of AI, and especially if we want systems that intervene, so for agents, for example, they need cause-effect knowledge. Absolutely.
Mhm. Okay, we have two questions from the audience. So quickly, so from Divya Sitani, what causal discovery or causal inference checks should we include in a foundation model embedding-based clinical prediction pipeline?
Well, I don't know. I cannot answer that. I'll be glad to answer that, to try to answer that by email if you want. I don't know.
Okay, next one.
Complicated
So
question.
from Muhammad Ali Jawhar, are knowledge graphs as a possible solution to the lack of causal discovery or reasoning capability in LLMs?
Yeah, I think partially yes, because LLMs. So there are areas in some areas. I recently was in a PhD defense that using this, which are kind of mixing symbolic methods, which actually use graphs, knowledge graphs, with LLMs in areas which are very specific, where you can actually have knowledge graphs, which is maintenance, for example, maintenance of say communication networks. There's a huge knowledge graph that relates all sorts of variables that monitor the system, and they have very clear semantic meaning, and their relationship is very well known. But then you use some sub-symbolic methods, such as an LLM, to interact with this system and to ask questions and to probe the system. So I think there's some interesting feature for methods that use both these structural knowledge with non-structural, let me call it like that, LLMs and our chatbots.
All right. Thank you so much for those answers to the audience
Mhm.
questions and also my questions. So it was my great pleasure to moderate this, although you did most of the work, Mario. Thanks for that. And now I pass it back to the AI for Good team.
Okay, thank you. Thank you for being around.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.